Engineered Controls International Incorporated, the manufacturer of Rego products, presents Regulator Basics, an introduction to LP gas regulators. LP gas burners provide clean, efficient energy, but only when they receive a continuous supply of LP gas at a properly adjusted and maintained pressure. This gas is pushed into the gas system by the pressure of the supply container. However, pressures in the LP gas container will vary, and the system's gas demand will fluctuate. To ensure the burners operate properly, we must control these variables. It is the LP gas regulator that provides this vital control. It compensates for the container's pressure variations, which range from 220 pounds per square inch in very warm weather to 8 pounds per square inch in cold weather or when a large amount of gas is being used. The regulator also compensates for fluctuations in the system's gas demand. Demand can range from a maximum value when all burners are on to a minimum value when only pilot burners are lit, or to zero when electronic ignition systems are used. The LP gas regulator is truly the heart of the LP gas system, providing a continuous supply of gas to appliances and burners at a properly adjusted and maintained pressure. Let's take a closer look at a regulator. A regulator has three major elements. A rubber diaphragm, which senses the pressure of gas in the regulator. The diaphragm is connected to the lever actuator and seat disc assembly. The position of the seat disc controls how much gas enters the regulator. And finally, a simple compression spring, which provides the force or muscle to help control the delivery pressure with inlet pressure and gas demand variations. Here's how the regulator works. Gas, supplied by the pressure in the container, enters the regulator through the inlet nozzle. It moves around the seat disc and lever assembly and fills the area below the diaphragm. Gas then exits the regulator towards the downstream appliances. The pressure below the diaphragm pushes up against the spring's force above the diaphragm. This force controls delivery pressure. When the demand for gas downstream of the regulator increases, there is less gas pressure under the diaphragm assembly. With less force against the bottom of the diaphragm, the spring pushes the diaphragm assembly down. The flow of air through the bonnet's vent allows the diaphragm to move freely. When the diaphragm moves down, the lever rotates about the pivot pin, moving the seat disc further away from the inlet nozzle. More gas pressure is allowed into the regulator and downstream to the appliances. This increased pressure under the diaphragm causes the diaphragm assembly to move upward and compress the spring. When the force created by pressure below the diaphragm matches the force exerted by the spring, the diaphragm stabilizes, resulting in a constant delivery pressure. If the demand of gas downstream decreases, the gas pressure under the diaphragm assembly will increase. The diaphragm moves upward as the force created by the pressure under the diaphragm overcomes the force of the spring. Again, the open vent allows displaced air to exit and the diaphragm to move freely. The lever rotates about the pivot pin, moving the seat disc closer to the inlet nozzle. The flow of gas pressure into the regulator is now reduced. The diaphragm stabilizes when there is equal force on both sides. The regulator continually repeats the process, maintaining a constant delivery pressure. Single-stage regulation maintains delivery pressure within a relatively small range. Two-stage regulation, however, is much more precise. It compensates at both the first-stage regulator and the second-stage regulator, providing an even smaller delivery range. In addition to regulating delivery pressure, the regulator will also respond to other factors. The regulator is designed to lock up should the system's demand for gas stop. When this happens, the downstream pressure will build, rotating the lever arm and moving the seat disc towards the inlet nozzle until all gas flow stops. If any foreign material is caught between the inlet nozzle and seat disc, the regulator may not shut off completely. Gas would continue to flow, building downstream pressure to an excessive level. A relief valve, required in all final stage regulators, vents excess gas pressure when it reaches a predetermined level. The relief valve opens, allowing the excess gas pressure to vent out of the regulator. It is important that the regulator's vent has a screen and is clear and fully open at all times, allowing discharge outside. Obstructed vents could prevent the relief valve from operating properly, or prevent the diaphragm from moving freely, which can result in improper regulation. The regulator's vent must be installed facing down or protected so its operation will not be affected by the elements. Regular visual inspections are strongly recommended. By cutting away the ECII LV4403 series, we see the quality engineering that goes into all our regulators. These features include a relief valve that is built-in and tamper-resistant. A large bonnet vent equipped with a protective screen helps to prevent blockage. A rigid diaphragm plate is designed to help the regulator respond to very small changes in pressure and downstream demand. The molded diaphragm is made of twin layers of synthetic rubber, sandwiching a tough, flexible fabric. Sealed in a groove in the body and secured in place by the bonnet, this design provides highly sensitive response to pressure fluctuations. The lever and control linkage react quickly to diaphragm movements. The seat disc is made of durable material which seals easily. It moves perpendicular to the precision machined inlet nozzle, ensuring a good seal and minimizing uneven wear. Engineered controls, quality components, and designs help to ensure our regulators perform dependably. Each time the downstream demand increases, the diaphragm moves down and the seat disc moves away from the inlet nozzle, allowing more gas to flow into the regulator. When the downstream demand decreases, the diaphragm moves up and the seat disc moves towards the inlet nozzle, restricting the flow of gas pressure into the regulator. The LP gas regulator, constantly compensating for changes in inlet pressure and downstream demand, providing your appliances a continuous supply of gas at constant pressures. The LP gas regulator, truly the heart of the LP gas system. Engineered Controls International Incorporated, the manufacturer of Rego products, presents Regulator Basics Performance. The LP gas regulator is the heart of the LP gas system. It compensates for changes in inlet pressure and system demand, providing a continuous gas supply to the appliances and burners at the properly adjusted and maintained pressures. To understand the relation of inlet pressure and system demand on the regulator's delivery pressure, we look at its performance curve. The gas demand, or BTU capacity, is plotted along the horizontal axis. This is the amount of gas that is being consumed by the system. Delivery pressure is plotted along the vertical axis. This is the pressure measured at the outlet of the regulator. Then, at a specific inlet pressure, we can see how the system's demand affects the regulator's delivery pressure. These regulator boards enable us to control the variables of inlet pressure and demand. By plotting these variables with the regulator's delivery pressure, we develop a performance curve. Let's look at how the boards simulate an actual LP gas installation. The first component is a regulator connected to a source of gas. This regulator allows us to vary inlet pressure, displayed on this gauge. It is representative of inlet pressure seen in typical service. The next component is the regulator system. We can simulate either a single-stage or a two-stage system by moving these directional valves. This gauge shows the gas delivery pressure of the first stage regulator in the two-stage system. The water manometer is the third element. It reads the delivery pressure of the final stage regulator in inches of water column. On our second board, each valve handle, when opened, allows flow through a different size orifice, simulating different gas demands. The first orifice is equivalent to a 75,000 BTU per hour flow. The second, 175,000, then 250,000, 350,000, and 500,000. These are representative of the demand or BTU capacity of the system. These variables, inlet pressure, delivery pressure, and system demand, are then plotted, providing the performance curve. Let's create an actual performance curve for a single-stage regulator, the ECII LV4403C series. The first step will be to find the set point of the regulator. By looking in the L500 catalog, we see that the setting of the regulator is 11 inches of water column at an inlet pressure of 75 psig and a system demand of 75,000 BTU per hour. By adjusting our system to these conditions, 75 psig inlet pressure and 75,000 BTU capacity, we find the regulator does deliver 11 inches of water column, the original factory setting. We then mark this point on the graph as our set point. Next, we find the regulator lock-up pressure. If the system's demand drops to 0, the regulator is designed to completely stop the flow of gas. This is referred to as regulator lock-up. This lock-up pressure should only be slightly above the outlet pressure. UL requires it not to exceed 120% of the factory setting, or in this case, 13.2 inches of water column. Here, the lock-up pressure is 12.8 inches of water column, well within the required range. We mark the regulator lock-up as our next point on the performance curve. If a regulator has a high lock-up, does not lock up, or is creeping, it's often the result of foreign material on the seat disc which prevents complete seating. This condition is often resolved in the field by removing the inlet nozzle and cleaning the seat with a clean, dry cloth. Follow the instructions in the catalog and technical guide 109 to solve problems with your regulator's lockup. We continue the performance curve by creating different system demands for our given inlet pressure of 75 psig. At 175,000 BTU per hour flow, we find the regulator's delivery pressure is 10.7 inches of water column, and we mark this pressure directly above the BTU capacity. We repeat this procedure for each capacity, marking the delivery pressure reading. At 250,000 BTU per hour demand, delivery pressure is 10.5 inches of water column. At 350,000 BTU per hour, it is 10.3 inches of water column. And at 500,000 BTU per hour, it is 10.0 inches of water column. Now, by connecting all these points, we complete the first performance curve for the regulator at 75 psig inlet pressure. By adjusting the regulator's inlet pressure to different settings, we can simulate hot and cold weather conditions and provide different performance curves for the same regulator. For example, in hot temperatures, inlet pressure can reach 175 psig. The inlet pressure is adjusted to 175, and demand to 0, we find the lockup pressure is 14.2 inches of water column and mark it on the chart. We repeat this process for each flow condition, creating a new curve for the new inlet pressure of 175 psig. In cold temperatures, inlet pressure can go down to 30 psig. We can simulate this condition and create a curve for this inlet pressure. These performance curves for our single-stage regulator show that for a given inlet pressure, as demand on the system increases, delivery pressure decreases. The exact same exercise can be performed for a two-stage regulator system. Here, we use an ECII LV4403 TR series for the first stage and an LV4403B series for the second stage. The LV4403 TR series has a factory set delivery pressure of 10 psig. We now find the published set point of the second stage regulator by looking in the L500 catalog. At 10 psig inlet and 75,000 BTU per hour demand, the delivery pressure of the regulator should be 11 inches of water column. By simulating these conditions, we find that this regulator does read 11 inches of water column, the factory setting. We mark this point on the graph as our set point. By cutting the demand to 0, we find the lockup pressure for the second stage regulator of our two-stage system, 12.8 inches of water column, and mark this as the next point on our performance curve. With a 175,000 BTU per hour demand, the delivery pressure is 10.8 inches of water column. By simulating the different gas demands, a curve for the two-stage system with a 75 psig inlet pressure is generated. This can be repeated, simulating the same conditions plotted for our single-stage regulator. By comparing the single and two-stage performance curves, we see the two-stage system's curves are much flatter and they are closer together. This illustrates that in a two-stage system, varying inlet pressures caused by hot and cold conditions have a smaller effect on the system's delivery pressure than in a single-stage system, a result of gas going through two regulators. The first stage regulates inlet pressures down to 5 or 10 psig. The second stage regulates these lowered inlet pressures down to appliance pressure, normally 11 inches of water column. Two-stage regulation reduces the variations in delivery pressure caused by changes in inlet pressure. This is very important to the proper function of many high-efficiency appliances. Twin-stage regulators provide the same benefits of two-stage regulation in one compact unit. Using our regulator boards, we can simulate what happens in a system with undersized piping. By using the second water manometer downstream of the tubing before the flow valves, we can read the pressure on both ends of the line. This flexible tubing is properly sized. It simulates an installation with the correct pipe or tubing, causing less than 1/2 inch of water column pressure drop. Upon creating a flow of gas, we see the regulator's outlet pressure reads 11 inches of water column. The pressure on the downstream side of the tubing reads 10.8 inches of water column, within the 1/2 inch range. When we replace this line with a smaller, undersized line, we see what happens in an LP gas installation with undersized pipe or tubing. Here, we use tubing which simulates a 3/8 inch copper tubing which is being run for 10 feet. The delivery pressure, measured at the outlet of the regulator, is still at 11 inches of water column. However, the pressure downstream of the undersized line is now only 8 inches of water column, well below the allowable 1/2 inch water column drop. In order to compensate for the undersized pipe and increase the pressure at the end of this tubing back to at least 10.5 inches of water column, we must increase the delivery pressure of the regulator. In this example, we increase it to 14.5 inches of water column, well above its original set point. Now at zero demand, we see the lockup pressure at both points goes up considerably, well beyond its original lockup pressure of 12.8 inches of water column. Improper pipe size exaggerates regulator performance due to changes in demand and inlet pressures. This results in inefficient appliance operation, unnecessary readjustments, and costly service callbacks. You now have a basic understanding of how the performance curves for a regulator are developed, how they show the effect of inlet pressure and system demand upon the regulator's delivery pressure. You saw how two- and twin-stage regulation reduce the variations in delivery pressure, and an example showing the importance of proper sizing. Used properly, the LP gas regulator provides a continuous supply of gas at the properly adjusted and maintained pressures. The LP gas regulator is truly the heart of the LP gas system. Engineered Controls International Incorporated, the manufacturer of Rego products, presents Regulator Basics, Pipe and Tubing Selection. The LP gas regulator is the heart of the LP gas system, compensating for changes in inlet pressure and system demand, providing a continuous gas supply to the appliances and burners at the properly adjusted and maintained pressure. There is, however, another critical component of all LP gas systems, the pipe and tubing. Let's look at the steps involved in selecting the correct size pipe and tubing for your installation. To do this, you will first make a rough sketch of your installation. Next, determine the amount of gas that each individual section of pipe or tubing must be able to carry at their maximum loads. And third, measure the lengths between regulators and to the appliance farthest away. With the maximum loads of each segment and the lengths between the regulators and the appliance farthest away, you can use the available charts to determine the correct size of pipe or tubing. Let's look at an example installation to help us understand the process. This sample sketch represents a common domestic two-stage regulator installation with a first-stage regulator at the tank and second-stage regulator at the house. This installation has a furnace, a water heater, a range, and a clothes dryer. If any appliances are expected to be added in the future, they should also be included in your sketch to allow for the added load. Each appliance comes with a maximum load value listed by the manufacturer directly on the appliance. Here are some representative numbers for our example. We are now ready to find the maximum load value for each segment of our installation by adding the maximum loads for all appliances found downstream. For example, in first stage piping segment AA to A, all appliances are found downstream. Their total gives us a maximum load of 338,000 BTUs per hour. This is also the load for the first section of second stage piping, segment A to B. Segment B to C only has to carry the demand for the water heater, range, and clothes dryer. Adding these figures gives us 138,000 BTU per hour. Some segments only carry the load for one appliance. Section D to H carries only the load of the range. It has a maximum load of 65,000 BTU per hour. We continue until the maximum value is found for each segment in the system. A chart will keep our data organized. We must now determine pipe lengths for our calculations. With a two-stage system, we first measure the length from the outlet of the first stage regulator to the inlet of the second stage regulator. Here it is 26 feet. And then the distance from the outlet of the second stage regulator to the inlet of the appliance farthest away, the clothes dryer, giving us a distance of 58 feet. We can now add the pipe lengths to our chart and can begin to size the individual segments by using the appropriate sizing chart in the catalog. For piping between a first and second stage regulator, there are three charts. One for first stage regulators set with a delivery of 10 psig, one for first stage regulators with a delivery of 5 psig, and one for plastic tubing. This fourth chart is used for second, single, and twin stage piping. For our example, let's assume that the first stage regulator is set for a 10 psig delivery. We would use this chart. To select the correct pipe size, we use the length measured between the regulators, 26 feet, and the maximum load for the segment, 338,000 BTU per hour. We then find the column which corresponds to this length, or is the next longer length shown. Here, it is 30 feet. We look in this column for the value that is equal to or the next greater value to the maximum load. There can be a value for both copper tubing and pipe. With a maximum load of 338,000, we find a value for both. We follow these rows over and find we may use either 1/2 inch copper tubing or 1/2 inch pipe size. We can now begin our second stage pipe sizing using the proper chart and the distance to the appliance farthest away. This length is used for each and every segment in the second stage. In our example, this distance is 58 feet. The maximum load for our first segment of second stage piping, segment A to B, was calculated at 338,000 BTU per hour. We find the distance that corresponds to our 58 feet length, or the next longer length, here, 60 feet. Remember, in this example, we will use the 60 feet column for the remainder of our second stage pipe sizing. We look in the column for the value equal to or the next greater value to the maximum load. Using the maximum load of 338,000, we find there is not an appropriate value for copper tubing, yet find one for pipe size. We follow the row over from this value and find the sizing for this segment, 1 inch pipe. Our next length of pipe, segment B to C, must carry a maximum load of 138,000. Using the same 60 feet column, we locate the values that are equal to or the next greater values to this maximum load. Follow the rows over and find that either 7/8 inch tubing or 3/4 inch pipe will handle this demand. We continue this process using only the one column determined by the length from the second stage regulator to the appliance farthest away, in this example 60 feet. We select the correct size of pipe or tubing for each line segment in the installation. In a single or twin stage system, the pipe sizing procedure is similar to that used for the second stage piping of a two-stage system. We add up the maximum load for each segment of pipe and measure the distance from the single or twin stage regulator to the appliance farthest away. This one distance is used for each calculation. We then use the appropriate chart to size each segment in the system. By comparing the sizes needed for the two-stage and single-stage systems, we discover that two-stage systems can often provide a cost savings in piping. This is a result of the difference in pipe size. In a single-stage system, the line running from the container to the appliance must be large enough to transmit gas at a low appliance pressure. However, in a two-stage system, the line between the regulators can be much smaller since the first stage transmits at a higher pressure and is reduced down to appliance pressure at the second stage regulator. Often the reduced cost of piping in the two-stage system will pay for the second regulator. giving you more precise regulation, uniform delivery pressure, and reduced freeze-ups for the same or less money than a single-stage system. Let's review the steps you will go through to choose the proper pipe size for your installation. First, make a rough sketch of your installation, including all current appliances and allowances for future appliances. Second, find the maximum load for each segment of pipe or tubing. Third, measure the lengths between regulators and to the appliance farthest away. Fourth, use the appropriate sizing chart from the ECII catalogs, the Serviceman's Manual, or the slide charts. Fifth, find the proper length in the appropriate table. Sixth, find the values in this column that are equal to or are the next greater value to the maximum load value for each pipe segment. And last, follow these rows over and read the correct pipe and tubing size. Following these steps will help you select the correct pipe and tubing for your installation. This, combined with the proper ECII regulator, will ensure that your LP gas system has a continuous gas supply at the properly adjusted and maintained pressure.